Approximating areas under curves using rectangles. Imagine a car traveling at a constant velocity of 60 miles per hour along a straight highway over a 2-hour period. Using v of t equals 60, find the displacement of the car from t equals 0 hours to t equals 2 hours. The displacement will be 120 miles. This is what I want you to notice. The displacement is the same as the area under the velocity curve from t equals 0 to t equals 2. So area under a velocity curve gives displacement. Area under a velocity curve gives displacement. Let's do another example. Suppose the velocity in meters per second of an object moving along a line is given by v of t equals t squared, where t goes from 0 to 8. What's going on now is that your velocity is changing. So you don't get an exact value, instead you get an estimate, and what you do is you estimate the area under the curve using rectangles. And here we have 3 different estimates. Notice that as you increase the number of time intervals, you improve your approximation. In upcoming sections, we're going to increase the number of rectangles indefinitely using a limit process. For this problem, we're going to use n equals 8 rectangles, where the height of each rectangle is going to be determined by the midpoint of each time interval. This is called a midpoint Riemann sum. If we use 8 rectangles, each rectangle will have a time width of 8 minus 0, so that's the length of the time interval, divided by 8, the number of rectangles. And so each time interval will be 1 second. We then find the midpoints of each time interval. And notice that we can express the midpoints using a formula. Since velocity is the square of whatever time it is, the velocity at time 2k minus 1 over 2 will be 2k minus 1 over 2 quantity squared, and that's meters per second. So, for example, at time 5 over 2, the velocity is 25 over 4. And the displacement, we estimate that between t equals 3 and t equals 4, we estimate the displacement to be 6.25 meters. So that's just an estimate using a rectangle. Likewise, we estimate that between t equals 5 and t equals 6, the displacement, we estimate the displacement to be 30.25. Displacement during the kth interval is going to be 2k minus 1 over 2 quantity squared, and that's in meters. Total displacement would be adding up each one of these 8 rectangles. And total displacement is estimated to be approximately 170 meters. Using 8 rectangles, we get 170 meters for the displacement. However, you can see if we had used 64, then we would have gotten a slightly larger number. But you can see that as the number of rectangles increases, we seem to be converging to a value. Let R be the region bounded by the graph of f of x equals x to the third plus 1, and the x-axis between 0 and 2. Approximate the area of the region using a right Riemann sum with n equals 50 subintervals. So we're going to use 50 rectangles. First, partition your interval into 50 subintervals of equal length. So each subinterval is going to be of width 1/25. Second, mark the subinterval starting with A being starting with your left endpoint of your interval. So x sub 0 is, in this case, 0. X sub 1 is 0 plus one interval of 1/25, and so on. The kth interval would be between k minus 1/25 and k/25. Continue marking your intervals until you get to the end point. For each subinterval, find the area of the associated rectangle. If we're using a right Riemann sum, we evaluate the function at the right endpoint of the kth interval. Next, add up the 50 rectangles, each with the area. So we're using the right endpoint, so we evaluate the function at k/25. So that's the height of the function, and then change of x, that's the width of your rectangle. Now the width of the rectangle, remember, is 1/25. And we did this summation in the previous video, and so I'm not going to run through it again. But for this particular problem, we get an approximate area of 6.1616. Take care. Have a great day.